afternoon, my name is Ben Holken. I'm a senior lecturer here in the School of Mechanical and Electronic Engineering at UTS, and this is the Vibration Lab. This video is to introduce the use of various different types of transducer that we use for measuring vibration. For example, this single axis accelerometer here, which is a device from Brulin Kier 4353B transducer. There are different types of transducer, like this microelectromechanical system transducer here, different type. We also have impact hammers, which are force transducers, essentially, and are similar in principle of operation to an accelerometer. I'm using an oscilloscope to be able to show you how these work today. There is a separate video available on the use of oscilloscopes. If you need to refresh yourself on how to use an oscilloscope, I suggest you do that. We connect the transducer with the appropriate type of cable. In this case, I've got a gold-plated copper cable here with a pin that needs to be very firmly but carefully pushed into the transducer, and then we close the shield, if you like, with the screw there, and we tighten this up firmly again. The O-ring goes into some slight compression and prevents this from undoing itself in the case of some vibration. So we want from the entire measurement chain, from transducer through the cable into signal conditioning and then into the oscilloscope for us to have good electrical integrity, and that allows us to do that. So these transducers we have to handle with great care. One thing we must be very careful not to do with these transducers is to drop them, especially onto concrete floors where we can introduce a very high acceleration level into the transducer, which will damage it, probably destroy it. And these sensors are worth thousands of dollars each, literally. So the way they work is there's a small piece of mass, normally in a heavy metal like tungsten, which is mounted or bonded onto a small piece of piezoelectric material. As the sensor vibrates, the mass moves inside of it and causes a force to occur on the piezoelectric material, which produces a charge in picocoulombs, typically of that order of magnitude. Inside of here also are some electronics, some signal conditioning electronics that convert that picocoulomb charge into a voltage output. A voltage is provided via an IEP power supply over the cable, and the electronics amplify the measurement and modulate that voltage such that the voltage can be measured back in the system that we're using, the acquisition system that we're making the measurement in. So as I tap the transducer, you can clearly see it's making a measurement of the vibration. Okay. In terms of the power supply, this is a 4-channel IEP power supply, which is powered by mains, plugged into 240 volts. We've got 4 different channels on here, and we can select between them to check the functionality of the channel, and each of the 4 channels are captured in a pair of BNC connectors here. So this one goes on the right, goes to sensor, and this one goes to the measurement system, which is an oscilloscope. Some other types of measurement systems, for example, this Siemens SimCenter SCADA's mobile acquisition system, which I'll describe in a subsequent video, has IEP signal conditioning built in, so we can use these transducers without this intermediate signal conditioning supply in that case. But for use with an oscilloscope, which measures in volts, we need to provide the signal conditioning amplification separately. There are other forms of this than this 4-channel. There are some that are in line and various other types. Another type of transducer that we have here in the laboratory is this MEMS-based accelerometer. Rather than just measuring alternating vibration signal levels, this measures also DC. So this will measure acceleration due to gravity. If I put it on a flat surface, you'll be able to see that it will measure 1 G of acceleration. If I invert it, and I need to be DC coupled for this, which I am, then you should be able to see, as I turn it upside down, a different measurement coming through, but we're not yet properly set up. I'm not powered, actually. Sorry. So I've got a separate type of signal conditioning system for these types of transducers that's connected. These are all connected with a D-sub 9-pin connector. These are fitted here. This is a 3-channel device, which is an internal protocol that we have. And this is also mains powered. And again, you've got inputs for the transducer and outputs to the measurement system. Here you can see I didn't have it powered up, so we weren't getting a signal on the oscilloscope. Now we have a signal. This is essentially 1G. If I turn this upside down, you'll see that I get minus 1G when I invert that transducer. 1G, minus 1G, plus any vibration that I apply to that transducer. Okay, so that's a DC measurement, DC acceleration measurement, AC acceleration measurement. They've got different specifications, they're fit for different purposes. They all come with a calibration certificate which describes their performance in terms of amplitude, linearity and phase response. They have a sensitivity in millivolts per G in this case, and in picocoulombs per G, sorry, I beg your pardon, in millivolts per G in this case, because this is an IEP type of transducer. So you have to consult the calibration certificate when you're interpreting the measurements that you make in volts, either with an oscilloscope, or you can put those sensitivities into the software system that comes with the acquisition system from Siemens to be able to measure engineering units from these transducers, measurements of G or of meters per second squared for acceleration. What else? I can show you also how to check and calibrate your transducer. So let's demonstrate this accelerometer calibrator here. This is essentially a shaker. It shakes or it vibrates at 159.2 Hertz at 10 meters per second squared RMS. And the reason for it being at 159.2 Hertz is that that corresponds to an angular frequency of 1000 radians per second. And because of the fact that it's 1000 radians per second, it means that 10 meters per second squared is the same as 10 millimeters per second, which is the same as 10 microns of displacement, velocity and displacement respectively. And they're just useful parameters or useful values for this device to provide vibration at. It's got a built-in accelerometer such that no matter how much mass we attach to the top of it, obviously within sensible limits, it will always produce 10 millimeters per second squared, or 10 meters per second, sorry, 10 millimeters per second of velocity, or 10 meters per second squared. So if I add, you can see here now we've got a measurement of of a certain number of volts here, and we could confirm that that was 10 meters per second squared. But if I add some extra mass, for example, to that, eventually the device, you can see it adjusting the level. If I apply a force, it adjusts the level. Eventually it will again give us 10 millimeters per second squared, or sorry, 10 meters per second squared. We use beeswax quite often to attach these devices to our structure. This is synthetic beeswax, so we only really need a very small amount of this. You essentially want a very thin film of beeswax, so you can see that I've attached that to the calibrator with beeswax. Sometimes we also use a stud mount, so here's a very small stud that's threaded on both ends. We can screw that into the transducer like this, and then into the accelerometer calibrator like this, or we could drill and tap our sample, or we could put a magnetic mount on our sample if it was metallic, and we can use all manner of different types of attachment, but the attachments should be suitable for the type of measurement. Beeswax is less stiff, let's say, than a physical stud mount. Sometimes we might use a two-part epoxy if it's staying on there for a long time. Other times you might use super glue, which is very good in compression and tension, but not very good in shear. So we can quickly remove a transducer if we've attached it with super glue by twisting it, obviously taking care not to damage the cable when we do so. How long have we been talking, please?
7.5.
Let's stop. Thank you.